Yeah. So, good evening, everyone. So, today we are going to discuss about the week 11 assignment of the previous year, which is assignment number 11 of the basic electronics course, which is EE62 NPTEL tutorial class. Okay. So, the instructor of this course is Professor Mohesh Patil from the IIT Bombay, and myself, Mr. Subhajit Basak. I am a PMRF fellow from IIT Bombay. So, this is our 11th lecture, 11th tutorial. So let's start. Okay. Yeah. Okay. uh, so today we will start about something known as so in the previous class we have already discussed about the basic digital electronics, the combinational logic circuit, and today we're going to discuss about the sequential part. So for the whole duration of the up till 10th tutorial we have already discussed about the analog electronics, the basic analog things, all the things like starting from the diode and then transistor, that is BJT, how it works as an amplifier, and then we have studied about some Bode plot, and then we have studied about the op amp, the basic op amp circuit, op amp with negative feedback and also op amp with the positive feedback, and then how the op amp can be act as an active filter, and then we have seen about the positive feedback which uh, so which is known as a Smith trigger configuration of the op amp, and then we have seen about the oscillator, and in the last lecture, week 10 lecture, we have started the digital electronics part. So as I have already discussed, just a second. Okay. Okay, so as I have already discussed that the digital electronics is divided into two parts, which is known as, the first one is the combinational logic circuit, and the second one is the sequential logic circuit. Okay. Yeah, just a second. Yeah. So first one is the combination logic circuit and second one is the sequential logic circuit. So I have already discussed the basic difference between the combination logic circuit as well as sequential logic circuit. In the combinational logic circuit, the current output, that is the present output, is a function of present input only. That means whatever is the input, based on that the output we have calculated, right? So we have already discussed about some logic gates, basic logic gates, and then the Boolean algebra, logic gates, and then the Boolean algebra, and then we have already discussed about the K-map, how to minimize and get the SOP expression, and also we have studied about some basic combination of circuit, suppose mask. Okay, so we have already discussed the mask, that is the multiplexer, and now today we are going to discuss about the sequential logic circuit. Sequential logic circuit. So in the sequential logic circuit, the basic element, the basic building blocks of the sequential logic circuit is the flip-flop, which is known as flip-flop. It is the basic building blocks of the circuit. Okay, so in the sequential logic circuit, what happens, the present output is not only function of the present input, but also it is a function of present input, the past input, and also the past output. Okay, first output. So this thing is known as the sequential logic circuit. So using the basic flip-flop, so basically in the digital electronics, in the sequential logic circuit, we have main two things, which is known as, one is known as latch and another is known as flip-flop. So there are basically some differences between the latch and flip-flop, so I will discuss one by one. So what happens, the the latch circuit is often known as asynchronous circuit. Why asynchronous? Because it has no clock signal, no clock. So asynchronous means it is not sync with the clock signal. Okay, in the where in the flip flop there is a synchronous circuit. So that means that is depends on the clock. So what is a clock? So clock is basically a periodic signal where for a certain amount of time the output is 1 and for another half of the time the output is 0. So this is known as clock. So it has some certain period which is known as clock period. Suppose after this waveform is repeating, so till this is known as a time period. So let us consider it as TC, time period of the clock. Okay, so the frequency of this signal, the frequency of the clock is nothing but 1 divided by TC, that is 1 divided by time period. Okay, 1 divided by time period. So this is the frequency of the clock. Okay, so we can see that in our laptop or anywhere in the digital system, laptop, desktop and any other digital system, we have a there is a specification of the clock frequency, that at how much speed the our actually the performance of the computer happens. Okay, so these are basically there it can work as 1 gigahertz speed or 1 kilohertz speed, depends upon the application. We generate the clock, and according to the clock actually the output changes, or the output of the calculation of the output happens. Okay, so there are certain types of clock, the triggering of the clock. So suppose first one is known as suppose this is a level triggered clock. So what do you mean by level triggered clock? So in the level triggered clock, there are two type of clock. One is the positive level triggered, and another is known as the negative level triggered. Okay, negative level triggered, negative level triggered. Okay, so what happens is this part of the clock is known as the positive level. Okay, this is positive level, and this part is known as a negative level. So what happens is when the clock signal is in this region, then whatever is the input, based on that the output varies or output changes. So this is known as a level triggered. Okay, so similarly we have another mode configuration which is known as edge triggered. So what happens in edge trigger? So similarly edge triggered has positive edge triggered clock, two types of edge triggered clock, positive edge triggered, and another is known as the negative edge triggered. Okay, negative edge triggered. So what happens, so during this cycle the clock, this cycle it was 0 and then it came to 1. Okay, and again from 1 to 0 it came 1 to from 1 it came to 0. So this edge is known as, from 0 to 1, this edge is known as the positive edge triggered, positive edge triggered. Okay, positive edge triggered clock, and this edge is known as the negative edge triggered clock, negative edge triggered clock. So what does it mean? That means that whenever the clock signal is changing from 0 to 1, if any circuit is positive edge triggered, then whenever the clock is changing from 0 to 1, then only it changes the output, or it calculates the output based on the input. It may happen that the output will be the same based on the input, but at this time is the deciding time when we consider that what is the input, and based on that what will be the output. Okay, in the similar manner, negative edge triggered is also a configuration where the clock when comes to 0 from 1, then the output is being calculated. Okay, so this is known as the negative edge triggered. Okay. Okay, basically the latch circuit is a asynchronous circuit. That means that has no clock, and in the flip flop this is a synchronous circuit, this has a clock. Okay, so we will solve one by one problem, and we will discuss elaborately that how the clock works and how we calculate the output based on the clock signal. Okay, so question number one. So it is a basically S bar R bar latch circuit. S bar R bar latch circuit. S bar R bar latch circuit. So the S bar and R bar are the input shown in the figure are applied to a NAND latch. So this is a NAND based latch. Okay, because NAND gates are used in this latch. Okay, NAND based latch. Okay, yeah. So NAND latch, assuming that Q is initially 0. So Q is at first it is 0. Okay, so which plot gives the correct waveform of Q? So what should be the Q if the S bar and R bar is like this? Okay, okay. Mm, so yeah, so this one. Okay, okay. I will draw this better. Okay, okay. So I am drawing again this NAND latch. So there it is known as S bar R bar latch circuit. So one input is S bar, another input is R bar. Okay, and the S bar is connected to the output Q, and R bar is connected to the output Q bar. Okay, and then there is a feedback path from Q. It is going to this NAND gate, and from Q bar it is going to this NAND. Okay, so this is the thing. So you should know that what is a NAND gate. We have already discussed. So in the NAND gate, what happens? We have already discussed in the logic gate part that if there is two input A and B and output is Y, Y is nothing but A B bar. Okay. So what is the truth table? So truth table of NAND gate is, this is the NAND gate. NAND gate. Okay. So 0 0 0 1 1 0 1 1. Okay, there are four possible combination of the A and B, and for here 0 0 the output is 1, 0 1 output is 1, 1 0 output is 1, and 1 1 output is 0. So we can say that the NAND gate has logical zero priority. Logical zero priority. What does it mean? So logical zero priority means whenever any of the input either A or B or AB both, whether any of the input is 0, the out irrespective of the other input, the output will be 1. Okay, so this has a logical zero priority. Similar is the case for the AND gate, right? In the AND gate also, whenever whenever any of the input or both the inputs are 0, then the output will be 0. But here NAND gate, it is the bubbled version of the AND gate. So this is the same thing, that is whenever any of the input is 0 or both the inputs are 0, then irrespective of the other input, the output is 1. So this is known as logical zero priority. Okay, so we will first uh, draw the truth table of the S bar R bar this latch circuit, and we will discuss. Okay, so S bar R bar, and then we have and then we have the next state and the next state complement. So see one thing, in here in the basic latch circuit and the basic flip-flop configuration, if one output is q, the other output will be the complement of that q. Okay, the complement of that output. Okay, the previous output. Okay, so here it is q, it is q bar. So what is happening, suppose s bar r bar, so this it has this 4 combination 1011. So what is the output, that is the remarks. Okay, so what is happening, look at this part first. S bar is 0, so we are applying here 0, and r bar is 1. Okay, so r bar is 1. So in previously it is it states in the question that assuming that q is 0 initially, so q equal to 0 it is initially. So if q is 0, q bar will be 1, right, as it will be the complement of q. So initially it is 1. Now what happens, whenever we are using this 0 input and this 1 output, the NAND gate has logical 0 priority. So whenever this NAND gate, the first NAND gate, this is first and this is second. Okay, this is second and this is first. Okay, so whenever this first NAND gate sees logical 0 in the input, so it will not wait for this input, but it will turn this thing into 1. Okay, output will be 1, and automatically if q is 1, the output will be 0 here. Okay, so that means that qn plus 1, this is 1 and this is 0. So this condition is known as set condition. Okay, set, that is, as q is 1, it is known as a set condition because it is set to 1. Okay, okay, for the second case it is 1 0. So for the second case, suppose it is 1 and it is 0. Okay, now see this thing, it is 1 and it is 0. So similarly the second NAND gate is seeing 0 at the input. Okay, so it will not see the other input, irrespective of that the output of this changes to 1, and as the out q bar is 1, so q will change to 0. So that means q is 0, qn plus 1, that is the next state, it is 0, and qn plus 1 bar, that is the complement, that is the 1. So it is known as a reset condition. Reset means as q is 0, so it is reset to 0. Okay, okay, so what happens when there is a 1 and 1 output, so 1 and 1, so here it is 1 and it is 1. So now in the first gate, one input is 1, this input is 1, and this input is also 1. So it will depends on this. Suppose this in q is 0 in at initial condition, so this 0 will come here and this output will become 1, and this output will then become 0 because this 0 is coming here. So this NAND gate output will be 1, right, because in the NAND gate we have seen that 0 1 the output is 1, so it will get the output as 1, and here the output will be 0 q. That means previously it was 0, then it is 0 again. Okay, similarly if it is 1 initially, suppose it is initially 1, so it is 0 at initial state. Then what happened, this 0 goes to here and that output will again become 1, and this output will be the complement of that, so it remains 0. That means whatever is the q, that remains the same. Okay, if the q is 0, it will remain at 0. If the q is 1, then it will remain at 1. So if s bar r bar is 1 1, then irrespective of the thing, the q remains the same of the previous condition. So this thing will represent by this, that qn plus 1, that is the next state, this is the next state, this is known as the next state. Okay, so this next state is depends, it is similar as the previous state. So qn means previous state, n plus 1 means next one, that is the next state. Okay, and this is the previous state, so it will remain qn bar. Okay, so these three things completed. Now s bar r bar, if both are 0 0, what happens? So if s bar is 0 and R bar is 0. So this first and second both NAND gate sees 0 in the one of the input, and as they both has a logical 0 priority, so the output will be 1. Qn plus 1 will be 1, and Qn plus 1 complement will also be 1. But this cannot happen, right? Q cannot be Q and Q bar, it should be complement to each other. So this state is known as invalid state. This state is known as invalid state. Invalid state. And here we can say in the remarks, this is no change or hold. That is, it is holding the previous output. Okay, so this why it is known as hold or no change. That is, nothing will change. The previous, whatever the previous condition, that will be the answer. So in the S bar R bar latch circuit, if there the input is 0 0, then we cannot say what will be the output, because Qn plus 1 is also becoming 1, Qn plus 1 also bar is also becoming 1. So it is an ambiguous state, so it is known as a invalid state. Okay, so this one you need to know. Okay. Okay, so this is the basic behavior of this S bar R bar latch circuit. Now we'll solve this question. So here what happens, this S bar and R bar has certain value. So I am okay, so I am trying to plot Q over here only. So this is T and whatever is the Q. Okay, yeah. So wherever the input changes, we put a dotted line here, because within that time we can decide whatever is the output. Okay. Okay, yeah. So here also it is, the input is changing. Okay, and here also the R bar input is changing. Okay, now we'll draw. Okay, so here it is the value 1, it is 0, it value is 1, this is 1, this is also 1, this is 1, but here it is 0, it is 1, here it has 1, it has the input 1, here it is 0, it is 1, here for this entire period it is 1 1, and then it becomes to 0, and then 1, it is 1, it is 1 also over here, and here also it's 1, it's 1, it's 0 here, and it's 1, and it's 1 here. Okay, so see how we'll draw this output waveform. So here the S bar and R bar is 1 1. 1 1 means 1 1. That is, whatever in this truth table, from this truth table, this is S bar R bar latch. Okay, so in from this truth table you can see, if the input is 1 1, the output is the in the previous condition. So it is already stated that assuming that Q is initially 0, that means if this 0 will be hold for 1 1 condition. Okay, so this is the 1 1. Okay, this thing, and then again it becomes 0 1, right? 0 1, then the output becomes 1, Qn plus 1, because we are OD about the Q, not Q bar, so Qn plus 1 is 1, so it will be 1 1 for 0 1, then it is 1 1 1 1 means again it will hold the previous condition. So previously it was 1, so after this thing it will also be 1, and then again it comes 1 0 1 0 means the output will be 0, that is a reset condition, so this will be 0, and then here it comes 1 1 1 1 means it hold the previous condition, that is previously it is 0 over here, right? So it will extend till this, and then again it has 1 0 1 0 means it is 0, so it will be 0 again, then it is 1 1 1 1 means hold the previous condition, so it will be again 0, and here it has 0 1. Okay, 0 1 means 0 1, that means set, it will set to 1, so here it switches to 1, and then here it has 1 and 1. Okay, 1 and 1 means it hold the previous condition, so previously it was 1 through the for this period, so it will continue. Okay, then it comes 1 0 1 0 means the output will change to 0, and then it is 1 1 1 1 means that is hold the previous condition, that means it was 0, so 0 will continue. Okay, so this is the output waveform of the Q. So the answer of this will be, there is a two pulse, right? So this one, but this one is big pulse, so this would not be answer, this will not be answer, this will not be answer. The correct answer will be answer B. So it is matching with this. Okay, so the correct answer will be option B. Okay, so this is the basic latch circuit and how we solve the problem. This is like this. Okay, yeah. So see one thing, this is why this is known as latch circuit, because it has no clock input. Okay, no clock input, that means it is asynchronous, that is not synchronous with the clock signal. If a circuit has don't have clock, it is known as asynchronous circuit. Okay, so I am moving to the next problem. Okay, okay, so this problem is about the JK flip-flop. The clock J and K waveform for a positive edge trigger JK flip-flop are shown in the figure. So if I draw the JK flip-flop, so how it can be drawn? So this is the NAND based JK flip-flop. Okay, I am drawing the NAND based JK flip-flop. So in the NAND gate, so if this 2 is input and then there is a Q and Q bar is output, so this two, there is this feedback path, and then as it is connected to here, it should be connected to here, and from Q bar there is a feedback path, and from Q there is another feedback path, and there is some clock signal. This is the clock and this is input J, this is K. So this is the basic configuration of the JK flip-flop. Okay, so how we can solve this thing? So at first we should know about the truth table of the JK flip-flop. Okay, so what is the truth table about the JK flip-flop? Okay, so here what happens, at first we have the input clock CLK clock, and then we have the input JK, and then we have Qn plus 1 and Qn plus 1 bar, and then we have some remarks. Okay, yeah. So how it works, if there is no clock, suppose the clock is 0, so it is a synchronous circuit because this is the JK flip-flop, JK flip-flop. So in the JK flip-flop, this is the synchronous circuit. Synchronous means that must have clock pulse. So that means with irrespective of the input, if there is no clock pulse, then the output will not change. The output will only change whenever there is a clock, otherwise the output will not change. Okay, so whatever be the output, if the output is changing but there is no clock signal, then the input is changing and there is no clock signal, then the output will not change or will not calculate based on the input. Whenever there is any clock signal comes, then only it will calculate that what is the condition of the input, that is the input variables, whether it is 1 1 or 0 1 or 1 0 or 0 0. Based on that it will calculate the output and it will reflect in the output. Okay, but if there is any no clock signal but the input is still changing from 0 0 to 1 0 suppose, or 1 1, then also it will not calculate and reflect in the output. If there is any clock signal, then only it will calculate the output. So when the clock is 0, irrespective of any input, the output will not change. That means the output will remain same. It is known as no change, or the hold condition. Okay, or the hold condition. Okay. Now suppose if the clock signal is 1, then four things can be available. One is 0 0, another one is 0 1, then it is 1 0, and then it is 1 1. So see one by one. Okay. Okay. Now the clock signals all are 1. Suppose this is 0 0. 0 0 means here I am putting 0, here I am putting 0. So it will come as 1 and then it will come as 1. So suppose this Q is 0, that means this 0 will come here, and as it is 0 it will be 1 initially. This is initial condition. So as this 0 comes here, it will be 1 and this will be 0 again. Okay, that means if the input is j is 0, j is 0 and k is also 0, that means this is a NAND gate. Okay, and we have already discussed this is a NAND gate. NAND gate has logical zero priority. That means if it sees any of the input as 0, then it will not detect any other input. Irrespective of that, the output will come as 1. So if it is 0 and 0, j and k, so both the NAND gate is seeing the 0 input, so the output will be 1, and then this 2 1 is being fed to the next stage. Okay, so this next NAND gate, so this input is 1 and this input is 1. Now suppose what I am telling, see, now suppose q is 0 initially q is 0, then this 0 comes here, and here automatically initially it will be 1 because it is complement, it is initially 0, it will be 1, and this one will come here. As this NAND gate will see 0 input, the output will be 1 immediately, and the other is the complement of that, that is 0. That means if it is 0, it will remain at 0. If it is 1, it will remain at 1. Okay. In the second case, what can happen? Suppose initially this is 1 and this is 0. So what happens? This 0 will go here and this one will come here. Okay. This one will come here. Okay. Not here. Not here. So this one will come here, and what happened, as it is seeing 0, then the output will be 1. Obviously the next one will be the complement of this. So that means if the previous input is 1, then the output is also 1, and here also it is also 0. That means whatever is the previous input, that is reflected in the output only when j and k is 0 0 and the clock is 1. Okay. Okay, so what happens? So here we can write that the output will be qn and it will be qn bar. So this is the same thing, that is no change or hold condition. Okay, now what happens? See, now the input is 0 1. Okay, so I am removing this thing. Okay, now what is happening? Suppose this is 0 and this is 1. So if this is 0, this output is 1. Okay, and if this is 1, and now the clock signal is also 1, so these two inputs are 1, so this immediately turns to 1. Okay, but this thing, suppose 0, it is 0 initially it is 0, and it is 1, so this 1 is being fed to input here 1, and this 0 is being fed to input here 0. So that means again that 0 will come. Okay, so what is happening now? This one and this one is come to here, and this 0 will come to here, so this will changes to 0 and this will changes to sorry, this will changes to 1 and this will changes to 0. That means that if q is 0 and if the output is 0 and 1, irrespective of the what is the condition, then the using this jk we can say that the output is 0 and this is 1. So this is known as a reset condition. Why reset condition? Because qn plus 1 is 0 now. Similarly for 1 0 it will come 1 and this is come 0. So this is the set condition. And for 1 1, what happens for 1 1? 1 1, suppose. So what I have already discussed, if this is 0 and this is 1, so this output will be 1, and as it is at first it is basically 0, so this 0 will come here and this will turns into 0 and this will turn into 1. But now in this case, if the input is 1 and 1, this is 1, okay. If now the this thing is 1 and 1, what happens? So this input is 1 and this input is 1, clock is also 1 1 1. Now if this is 0 and 1 initially, so this 1 is being fed to here and this 0 is being fed to here. So this 0 means this output is 1 and here the output will be 0, okay. So whenever this is sees a 0 and this output will changes to 1 and this will changes to 0. So same thing happens vice versa also. Suppose this thing is 1 and this thing is 0. Now this 0 goes to there and it will be 0. Whenever it sees 0 it will be 1, but here this q is being fed to this NAND gate, so this 1 is being fed to this NAND gate, so this output will be 0. And as it is 1 and it is 0, it has a this NAND gate sees a logical priority of 0, then the output will changes to 1 and this will changes to 0. That means if the previous input is 1 it will toggle to 0, and if the previous output is 0 it will toggle to 1 in the next step. So this is known as this will be qn bar and this will be qn, okay. So these things is known as the toggle or toggling step. So this is the basic truth table of the jk flip-flop, the j and k. So now we need so this is the jk truth table, okay. Jk flip-flop truth table, jk flip-flop truth table, okay. Yeah, so now we have now truth table. Now we need to calculate the output based on this. So see, here the timestamp is at this position, okay. I am extending this thing, okay. So this thing is known as edge triggered, positive edge triggered. Because why? Because at this timestamp only the output changes. That means if there is a clock only, then only it will see that what is the input as j or k. Before that also, if the input changes but the output will not change, output will change only at this clock pulse. After this clock pulse, it will detect and then it will change. So this is basically known as positive edge triggered, okay. Positive edge triggered flip-flop, positive edge triggered, positive edge triggered jk flip-flop. So this is known as positive edge triggered jk flip-flop, okay, because it will the output will calculate only in this positive edge. So now what will be the output? See, so at this positive edge, j and k was initially 0, that is j and k is initially 0. So that means whatever is the q, that will be the output, and q is 0 initially, so the output will be 0, okay. So 0, it will come to 0. And then in this clock pulse, what is the condition of the j? J is 1. See, this j changes from 0 to 1 before the clock pulse, but still in this time period the output will be 0, because the output will be calculated when there is a next positive edge coming, the next positive edge of the clock coming. Okay, this is 0 and here it is 1 and 0 at this position, at this instant. So that means 1 0, that means 1, the output will be 1, so the output will be 1. Okay, so 1. So see, in within this period this k changes from 0 to 1, but it will not changes in the output, because the output will only change whenever there is a clock pulse. Okay, okay. So here it is 1 and here it is 1. 1 1 means toggle. Toggle means previously it was 1, so it changes to 0. Okay, in this clock pulse, it is 0 and it is 1. 0 1 means reset, that is 0, so it will be 0. Again in this clock pulse it is 0, it is 0, so it will hold the same state, so it will be 0 again. In this clock pulses it is 1, it is 1, that means it will toggle according to the truth table, so it will toggle. And then here it is 1 and it is 1, so 1 1 means it will again toggle. Here it is 0, it is 0, that is it is hold the same condition, that is 0. And in the next clock pulse also it is 0 and it is 0, that it again hold the same condition 0. So the output will be like this. Okay, so option A is the correct answer. Option B is not, because in this period also it will be 0, it is wrong. And here also it is wrong, because in this period also it will be 0 and here also it is wrong. Okay, so the correct answer will be option A. Okay, yeah. So for this problem you have to solve the question like this. Okay, yeah. Now what is the minimum number of flip-flop, next question, what is the minimum number of flip-flop required for a mod 40 counter? So what do you mean by mod 40 counter? So mod 40 counter, that means it has 40 states, 40 states. So what do you mean by counter? Counter is basically count clock pulses, it counts the clock pulses, counts the clock pulses. It may happen that it can read each of the clock pulse, or it may also configured in such a way that it will alternatively count the clock pulse, or in the other way also. Okay, so for mod 40 counter means 40 states, so it will count 0 1 2 3 till 39, so it is known as mod 40. Why mod 40? Because suppose we are dividing something by 40, okay, any number, suppose 99, any number we are dividing by mod 40, so the output will be 40 to the 80 19, the modulus will be 19, this is known as modulus. Okay, this is known as modulus. So what can be modulus for mod 40 counter? Modulus means the remainder. Okay, so suppose we are dividing 109 using 40, so 40 to the 80 and then it will be 29, so 29 will be the modulus. Okay, similarly if it is 119 and it will be 80, it will be 39, so 39 will be the modulus. So similarly if 120, if we just divide 120, so there will be no, that is 0, 0 is the remainder, so 0 is the modulus. So that means for mod 40 counter, if it counts, it can count from 0 to 39, maximum is 39. So total 40 states, 0 1 2 3 4, like this 40 states are there. Okay, this consists of 40 states, 40 states. So this is known as the mod 40 counter. Okay, so mod 40 counter means 40 states. So suppose we have one flip flop, suppose this is D, this is Q, this is Q bar, and there is some pulse. Okay, there is some clock. Okay, so here what can be the output? If the input is for the D flip flop, this is the D flip flop, D flip flop, so what can be the output? If the input is 0, the output will be 0. If the input is 1, the output will be 1. So the output has two states, right? 0 and 1. So it has two states. So we can say this is a mod 2 counter. Mod 2 counter means the output can be comes as either 0 or 1. That is two state. One is 0, other is 1. So this is known as mod 2 counter. Similarly, if suppose two counters, if suppose there are two flip-flop cascaded, this two flip-flop is cascaded. So this is Q, suppose, and this is D1, Q1, Q1 bar, and then it is D0, Q0, Q0 bar, and it is connected like this thing or something like that. So the output can be Q1 and Q0. These two output can be either 0 0 or 0 1 or 1 0 or 1 1. So there are four states available. So the output will be either 0 or 1 or 2 or 3, right? 1 1 means 3, 1 0 means 2. So the output will be from 0 to 3. So this is known as it has four states, so this is known as mod 4 counter. So mod 4 counter means it can count from 0 to 3, that is four states: 0 1 2 3, four states. Okay, so similarly, so suppose there is a question like for to calculate the mod 4 counter, how many flip flops are required? So there is two flip flop is required. Okay, for to calculate mod 4, how we can calculate? Suppose 2 to the power n equal to 4, because each each flip flop has two states, 0 and 1. There are only, if suppose there are 2 bits for each flip flop, either it is 0 or it will be 1. So if there is a two states, so that means it is a mod 2 counter. Okay, so two states. So if it is cascaded with another thing, then we have four states, that is 2 squared equal to 4. This is 2 squared equal to 4, that is two number of flip flop. So how many number of flip flop? 2 to the power that number of flip flop represent the 40, mod 40. Okay, that represent the number of modulus, that is number of states. So here for this question, how many minimum number of flip flop required for the mod 40 counter? So 2 to the power n should be greater than 40. Okay, then only we can calculate this thing. Suppose if we use 5 counter, 5 flip flop, 5 flip flop to calculate. So using this 5 flip flop, how many states we can calculate? States we can calculate 2 to the power 5, that is 32. But if we use 6 flip flop, then how many states we can calculate? States, that is 2 to the power 6, that is 64. If there are 7 flip flop, then total number of states that we can calculate is 2 to the power 7, that is 128. If there are 4 flip flop, then the total number of states that we can calculate is 2 to the power 4, which is 16. So here we have to calculate the 40 states. So using this 5 flip flop we can calculate only 32 states, but using this 6 flip flop we can calculate 64 states. So among these 64 states you can easily calculate the 40 states also. So how much minimum number of flip flop is required? It is, and the answer will be 6. Using the 7 number of flip flop also we can calculate the 40 different states, but as we need the minimum number of flip flop required, so that will be 6. Using 5 we cannot calculate, we can calculate only 32. So it is required for a mod 32 counter, but greater than mod 32, that is mod 33, mod 34, such that for mod 40 till mod 64 we have to use minimum 6 number of flip flops. Okay, so 6 will be the answer. Okay, so the next question, it is a very easy one. So here, given that Q3, Q2, Q1 and Q0 is 1100 initially, what is the state of the counter shown in the figure after 5 clock pulses? Okay, so here we have, this is a synchronous circuit, this is a synchronous circuit. Why synchronous? Because all of these flip flop, all of these are D flip flop. Okay, all of these D flip flop are synchronously connected with clock. Okay, so whenever there is a clock high, then this flip-flop output will change. At the same time, these other three output also will also change. Okay, each of the D flip-flops output will change. Okay, so this is known as a synchronous circuit. Okay, so we have to know basically what is the D flip-flop and how the truth table will look like. So this thing is basically a D flip-flop Q, and this is Q bar, and the input is D, and obviously there is a clock. So this is a clock. Okay, so remember one thing, if suppose so in the clock signal we have already discussed, the suppose this is a clock signal, that is a repetitive signal, this width also need to be same. Okay, so this width are also always the same. Okay, this thing, the time period, this is T, this is T, this is T, the same thing. Okay, yeah, if this is a clock signal, then I have already discussed that this is the positive level and this is the negative level, this is the positive edge and this is the negative edge. So if the output changes during this time, this is known as positive level triggered, and that clock signal is represented by this is known as positive level triggered, level triggered type of clock. Okay, clock, type of clock. So this is the symbol. If there is negative level triggered, so that can be shown by this bubble sign. So that means it is negative bubble trigger, negative level triggered. Okay, if there is positive edge triggered, positive edge triggered, so that can be represented by this clock symbol. Okay, and if there is negative edge triggered, if there is negative edge triggered, then it is, there is a bubble in front of this arrow. Okay, that is represented by this. So now we are using this negative, suppose we are using this negative edge triggered. Okay, okay, so now what is the truth table of the D flip flop? That is clock D and Qn plus 1, right? So if the clock is 0 irrespective of the D, the output will be the same, output will not change. If the clock is 1, then if the input is 0, then the output will be 0, and if the input is 1, the output will be 1. So whatever is the Qn plus whatever is the D, that is reflected in the next state, Qn plus 1. Okay, okay, now we have to write, we have to see that uh, what is the answer of this question. We have to calculate this thing. So here from this thing we can see that the D0 in the next cycle, what happens, this D0 is being fed in the next cycle, the D0 is equal to Q1, D1 is equal to Q2, D2 is equal to Q3, and D3 is equal to this Q1 and Q2, NAND of Q1 and Q2. So Q1, sorry, Q1 and Q0, Q1 and Q0, this NAND operation. Okay, so if we write a truth table over here, that means if for next clock pulses what happens, then what we get, see here in the question is, sorry, here in the question is Q3, Q2, Q1, Q0 was 1100 initially. What is the state of the counter after 5 clock pulses? Okay, so I will write clock pulse over here. It clock pulse I am making one table. Then I have D3, D2, D1, D0, and again we have Q3, Q2, Q1, Q0. Okay. So what happens after first clock pulse? Okay. What happens? At first it was at first Q3, Q2, Q1, Q0 will be 1100 initially. So it is 1 1 0 0 at the initial condition. Now what happens in the first clock pulse? 1, number of clock pulse 1, this is 0. Okay, so the 0, the output is this. And then what happens, whatever is the Q1, that is goes to D0, that is 0. D1 is Q2, that is 1. D2 is Q3, that is 1. And now this is Q1 Q0 bar, Q1 Q0 bar, that means it will be 1. Okay, and then in the next clock pulse, as it is 1110, the same thing will appear here, because we have already know that Qn plus 1 is equal to D, right? So this 1110 will come here automatically. Okay, this is after the first clock pulses. After the second clock pulse, what happens? So this 1100, now this D0 is equal to Q1. So D0 is equal to Q1, so that means this is 1. D1 is equal to Q2, D2 is equal to Q3, and D3 will be Q1 Q0 bar. Q1 Q0 bar means 1 into 0 bar, that is 0 bar, that means 1. So if it is 1, the output will be 1 1 1 1. Okay, so this is the second option. Okay, the third thing is, so I am writing this thing here. Actually D1 is basically Q1, it is basically Q2, it is basically Q3, and it is Q1 Q0 bar. Okay, okay, now see how what happens after the third clock pulses. This will be transferred to 1 1 1, and then it is Q1 Q0 bar, 1 into 1 bar, that means that will be 0. So it will be 0 1 1 1. Okay, and next in the fourth cycle it will be, then again it will be 1 1 0, that is it will be 1, because D0 is Q1, then 1, this is 0, and again it will be 1 1 part, that is 0. So it will be 0 0 1 1. Okay, and then again the fifth clock pulses, this one D0 will be 1, and this 0 will be 0, this will be 0, and here 1 into 1 dot 1 bar, that is 1 and 1 bar, that becomes 0. So the output will be 0 0 0 1. So according to the question, it is being asked what is the output of the counter after 5 clock pulses. Okay, after 5 clock pulses, after 5 clock pulses, the output will be Q3 Q2 Q1, this thing, Q3 Q2 Q1 Q0 will be 0 0 0. So the correct answer will be 0 0 0. So option B, the correct answer. Okay, yeah. Similarly, if we move to the next question, what is the modulus number of the counter in question 4? That is the same thing in this question 4. What is the modulus? Modulus means then we have to modulus means different state, right? So modulus means number of states. So what are the number of different states that we can calculate using this counter configuration? Okay, so how we can do? So we have to see some different. So here there is no repetition. First one is 1100 1110 1111. So there is no repetition. So till repetition we have to find that after how much iteration, how much clock pulses this iterates. Okay, so here what it is happening, so it is 0001, so now it will be 000, and 0 and 1 bar it will be 1, that means it will be 1000. So it is not repeating again, it will be 100, that is it is 1 0 0, and then 0 and 0 bar, that means it will come 1, so 1, so this is 1 1 1 0 1 1 0 0. And again if we go for the 8th clock pulses, so then this will be 1 1 0 1 1 0 and 0 0 1, that means 1, that is 1 1 1 0. Okay, so we can see that this 1 1 1 0, this repeat after 1 clock pulse, 2 clock pulse, 3 clock pulse, 4 clock pulse, 5 6 7 8. Okay, see, so now after how many clock pulses it happens, so for this thing, suppose 1 1 0 0, this thing we are this thing after how much clock cycle it happens, so it happens after at this time. Okay, so how many clock pulses, calculate, this is basically 1 2 3 4 5 6 7, so 1 2 3 4 5 6 and then again 7. So after 7 clock pulses, this value changes. So what are the number of different states? This is the 1 2 3 4 5 6 7. So 7 number of different states, 7 number of states, that means the modulus is 7, or the mod 7, modulus is 7. So the correct answer of this will be, what is the modulus number of counter question for this is the correct answer, the modulus number will be 7. Okay, yeah. Okay, moving forward to the next question. Consider the BCD counter shown in the figure. Okay, BCD counter is shown in the figure. Define D to be the decimal number corresponding to the binary number DCBA, where D is the MSB and A is the LSB. Okay, we want to design decoding logic such that X equal to 1. So we have one more logic circuit, which is the decoder, something decoding we are. So the X is equal to 1. So X is equal to 1 for D equal to, means the decimal value equal to 2 4 5 6, and X is equal to 0 for D equal to 0 1 3 7 8 9. Okay, and X is equal to don't care, this is the don't care, the value of D from 10 to 15 should be treated as don't care. So for D equal to 10 to 15. Okay, so these are the things. What is the minimum sum of products expression for X? So we have to calculate the what is the minimum SOP. So to calculate the minimum SOP, we have to solve the K-map. Okay, so it should strike in your mind, okay, that if we have to calculate the minimum sum of product, so we have to use the K-map to reduce the expression. Okay, you have to actually trigger this thing in your mind. Okay, so at first what is happening, the BCD counter, so BCD counter means binary coded decimal, binary coded decimal. That means if we are giving, so binary coded decimal, that means if you are giving anything, suppose 0, so it can be coded in binary 0. If you are giving 1, so it will be 1. If you are giving 2, it will be like this. If you are giving 3, it will be like this. So like this it happens, it is known as BCD, that is binary coded decimal. So now what is it is telling, that now after this BCD counter, this bits got changed. Okay, DCBA. So now it was ABCD, now it changes to DCBA. So it will be 0 0 0 0, then it will be 1 0 0 0, this will be 0 1 0 0, this will be 1 1 0 0, like this it happens. So actually to solve this thing, and then we have applied any logic circuit, that is an decoding logic, such that the x is equal to 1 for 2 4 5 6, 0 for 0 1 3 7 8 9, and for the rest of the conditions all are the don't care. Okay, so now we have to solve the k map and find the expression. So now to solve the k map, so at first we should draw the k map. So now as it is changes, a b c d, d is the MSB, so we should write D here, C here, and then B here, and then A here. So this is 0 0 0 1 1 1 1 0. We have already done this K-map solution in the previous week. Okay, 1 1 1 0. Okay, okay. So now you can also write here, this is 0 0 0 0. So it means this box is about 0. This box is about 0 0 0 1, that is 1. This is 0 0 1 1, that means 3, and this is 2 0 0 1 0, then 0 1 0 0. Okay, 4, this is 5, this is 6, this is 7, and then it will be 8, it will be 9, it will be 10, it will be 11, and it will be 12, it will be 13, it will be 14, and it will be 15. Okay, now we have to write that for 2 4 5 6, 2 4 5 6, that will be 1, and then 0 1 3 7 8 9, 0 1 3 7 8 9. For this all the things, all the x is 0, and then x equal to don't care for 10 to 15. So this is the 10 11 12 13 14 15. So now we have to get that what is the minimum sum of product expression. Okay, so we should form a group. So how we can form a group? So at first we try to make a group of 16. So group of 16 is not possible because some are 0. Now we want to make a group of 8. Group of 8 is also not possible from here. Okay, so now we want to form a group of 4 using the don't care. So we get this thing, and another we get this thing, group of 4. So here one more group can be formed, but all the ones are already taken, so we should not form any other group using this don't care term, that is don't care number 11 and don't care number 14. So these two groups are sufficient. So one is this group and the other is this group. Okay, so for this group basically the minimized expression is, this is a C, this is C, and this is B bar, this is B bar, and for this also this group, this value is B, this is A bar. So we can write that y is equal to, that is output, y not y, it is x, right? X is given, right? X is the output of the logic circuit. X is the output of the logic circuit. So that means the x is equal to, the x is equal to, this is A bar B, A bar B plus B bar C. So that will be the, so correct answer will be option B, right? Because it is B bar C, A bar B. Yeah. Okay. Yeah. Moving to the next question. Consider a 3-bit binary up counter with output Q2, Q1, Q0, Q2 being the MSB and Q0 being the LSB. 3-bit binary up counter. Okay. So if we draw 3-bit binary up counter, So this is basically a 3-bit binary up counter. Here we have T2, suppose Q2 bar. This we are giving as 1. This is asynchronous counter which I am drawing. Okay, because the clock is not synchronous with the same for the same flip flop. Okay, so there are several different flip flop. T1, suppose T1, it is Q1, and then it has Q1 bar, and then again it is Q0, it is Q0 bar, and this output is 1. This is 1, this is 1. So suppose this is a black box. Okay, we can design this as a synchronous counter, asynchronous counter, that doesn't matter. Okay, you can also form the synchronous counter also. Okay, up counter. Synchronous means the clock pulse will be with the same clock pulse will be fetched to each of the blocks or each of the flip flop. Okay, yeah. So now what is happening, it is telling like so consider 3-bit binary up counter with Q2, Q1, Q0, the Q2 and then Q1 and then Q0 to be Q2 being the MSB and then Q0 being the LSB. Okay, one second. Okay, so this will be T0, Q0, Q0 bar, T1, and this will be T2, Q2, Q2 bar. Okay, let's form the up counter. Okay, so Q2 being the MSB, so this thing is MSB and Q0 will be the LSB. Okay, from the counter output, the logical function x equal to Q2 Q1. So that means this Q1 and this Q2 passing through the AND gate, and it is formed X. So if the clock frequency at 8 kilohertz, what is the frequency of the X waveform? What is the frequency of the X waveform? Okay. So how we can calculate that what is the frequency of the this waveform? So we can see here that this if we draw the truth table, so Q2, Q1, Q0, and then here we have the value of X, that is Q2, Q1. Okay, so it is first up counter, so 0 0 0, it will start from 0 0 0 and then it will count 1. This is 0, then it will count 1, then it will count 2, then it will count 3, then it will count 4, this will count 5, then it will count 6, and then it will count 7. So what is Q2 into Q1? This will be 0, 0 into 0, this is 0, this is 0, this is 0, 1 into 0, this is 0, this is 0, this is 1, this is 1. So if we consider the clock pulse like this, so suppose this is a clock pulse, H trigger clock pulse. So here the output will be 0 0 0 0 till the 5 clock pulses. So that means this is the first clock pulse, second clock pulse, third clock pulse, fourth clock pulse, fifth clock pulse, and then it is 1 and then 1, and then it will again repeat to 0 0 0 0 like this. So that means throughout this thing, this is 0 0 0 0 0 and this is 1 and 1. Okay, okay, so okay, so here it also is 0. Okay, and the same thing. So here we can see that this whole thing will again repeat after this 8 7 clock pulse. That is 8 clock pulses. Okay, this is the first clock pulse 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So after 8 clock pulses it will again repeat and it will again from 0 0 0 0 0 0 and then 1 1. Okay, so that means that means this x, that is time period of x, is equal to this time period of x is equal to 8 times of the clock period of the clock. Okay, so 8 time period of the clock. So the frequency of this x will be 1 divided by time period, so it will be 1 divided by 8 tc. That means fc divided by 8. What is the clock frequency divided by 8? And here in the given question the clock frequency 8 kilohertz, so 8 kilohertz divided by 8, the correct answer will be 1 kilohertz. So 1 kilohertz will be the function of x equal to q2 q1. So the correct answer is option A. Okay, so this was a easy problem. In the next problem, consider a 3-bit binary up counter q2 msb and q0 lsb form the counter outputs a logical function. Now it is formed q1 q0. So if the clock frequency 8 kilohertz, what is the frequency of the x waveform? So here only I am doing this thing. Now the output x is equal to q1 q0. So if it is q1 into q0, it will be 0, it will be again be 0, it will be again be 0, it will be again be 1, it will be 0, it will be 0, it will be 0, it will be 1. So see, there is some periodicity 0 0 0 1 and then 0 0 0 1. Okay, so if we draw this waveform, these are suppose edge triggered, positive edge triggered, and what happened after 6 clock pulses it turns into 1. Okay, in the previous case, but here it is first clock pulse it is 0, so first clock pulse it is 0, then again 0, then third clock pulse it is 0, and fourth clock pulse it is 1, then again 0 0 0 and then again 1. And then if it has one more clock pulse, if we so, so that means it will be 1 and again it will be 0, again 0, this thing. So it will be 0 0 0 1 and again it will be 0 0 0 1. So after this is the time period, this is the time period of x. Okay, q1 q0, that is time period of x. So time period of x is equal to 4 time period of clock. Okay, because this one is time period of clock. So 1 2 3 4, 4 time period of clock, 4 into time period of clock. That means the function of this is 1 divided by tx equal to 1 divided by 4 into tc. That means fc divided by 4. Now it is given in the question fc is 8 kilohertz, so dash divided by 2, this becomes 2 kilohertz. So the correct answer will be 2 kilohertz. So what is the frequency of the x waveform? This is 2 kilohertz. Okay, so this is the answer. Okay, so the next question, The next question is, if the initial states of the counter shown in figure Q2, Q1, Q0 is 0, 0, 0, what is the state after 3 clock pulses? Okay. So see, how to solve this problem. This is a JK flip-flop and we have already know the JK truth table. So we should first know about the JK truth table. So in the JK truth table, JK Qn plus 1 and Qn plus 1 bar, it is 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 means it will remain the same. 0, 1 means it will be also 0, 1. 1, 0 means it will be 1, 1, and 1, 1 means it will be toggle. Okay. So this means this is remarks. If we put it at remarks, this is no change at first, and then it is set, then it is reset, and then it is toggle. Okay. Yeah. So now we should see what is the input over here. So here it is a J0. Okay, J0 K0. It is J1 K1. It is J2 K2. So we can write that. So we can write that what is the value of J0 and K0. We can write that this J0 and K0 is equal to 1 always, right? J0 K0 is equal to 1, and then J1 and K1 is equal to Q0 complement. Okay, Q0 complement, and J2 and K2 both are equal to, this is Q1 complement, it is Q0 complement, it is Q1, it is Q2 complement. So Q0 complement, Q0 complement into Q1 complement. This is the thing. Okay. So if we make a chart over here, this is the clock pulse. Okay. And then we make J2 K2, J1 K1, J0 K0, and Q2 Q1 Q0. Okay. So what is in the question, that in the initial state Q2 Q1 Q0 is 0, 0, 0. So that means it is 0, 0, 0 if there was no clock pulses. Okay. So now what happens? The J0 K0 is in the next clock cycle, it is 1, 1. So this is the first clock cycle, clock pulse 1. So it is 1 and 1. Okay. J1 K1 will be Q0 bar, Q0 bar, that means 1, 1. So it will be 1, 1. And J2 K2 will be Q0 bar, Q1 bar. Q0 bar is 1 into 1. Okay. So it will be 1, 1. So that means if J2 K2 is 1, 1, that means this will toggle. So Q2 will toggle 1, toggle. And then Q1 it will also toggle 1, and J0 Q0 is 1, 1, that means it will also toggle. In the second clock pulse, what happens? J0 Q0 is fixed, that is 1, 1. J1 K1 is Q0 bar, that is 0, 0. And J2 K2 is Q0 bar, Q1 bar. Q0 bar, Q1 bar is 0. So it will be 0, 0. 0 means no change, that is it will be same, it will be same. Now it will toggle. After the third clock cycle, what happens? This is 1, 1 always, and now J1 K1 will be Q0 bar, that means it will be 1, 1, and J2 K2 bar is equal to Q0 bar, Q1 bar, that is 0. So it is 0, 0. So this 0, 0 means it will remain the same. 1, 1 means it will toggle, and also it's toggle. Okay. So what is the question? What is the state after 3 clock pulses? So after 3 clock pulses, the state is 1, 0, 1. So this is the answer. Okay. 1, 0, 1. This is after 3 clock pulses. Okay. So the correct answer will be 1, 0, 1. So option C. Okay. So you can see that how we can solve this problem. Okay. In the next question, if the initial condition of the state of the counter is q2 q1 q 0 0 0, what is the state after 5 clock pulses for the same question? So I have to extend this thing then. So after 4 clock pulses, okay, I will just extend this thing. Okay, okay, so these are 1 1. This will be q0 bar, q0 is 1 bar, that is 0 0, and then this z2 or k2 will be q0 bar, q1 bar, that is 0 1, that is 0 0. So that means it will be same, but it will toggle. And after 5th clock pulse, it is 1 1, and then the j1 k1 will be q0 bar, that is 1 1, and here it will be q0 bar, q1 bar, it will be 1 1. So everything will toggle, this will be 0 1. So after the 5th clock pulses, the output will be 0 1 1. Okay, so the correct answer will be 0 1 1. So option D. Okay, yeah. Okay, now in the next question it is asked, what is the modulo number of the counter described in question 9? Modulo number. So modulo number means modulo number, that means modulus. So we have to find the modulus. Modulus means number of states, so how much number of states this flip-flop can calculate? Okay, that we need to determine. So how that can be determined? See, so as this is a modulus, that means, so we have to see the periodicity or the repetitive nature of the output. So when the output will repeat, then we will stop this calculation. Okay, so I will, now I am extending this calculation. So now previously it was 0 0 0, so it is not getting 0 0 0 anymore. Okay, so when it will get 0 0 0, then I will stop. Okay, so 6 clock pulse, after 6 clock pulse, what is happening? So this is already 1 1, and this is q0 bar, that is 0 0, and this is q0 bar, q1 bar, which is 0 0. So that means it will remain 0, it will remain 1, and it will change 0 1 0. Now also it is not repeating. After the 7th clock cycle, what happens? This is becomes 1 1, and it is q0 bar, that means it will become again 1 1. Very good. And in this thing, this q0 bar, q1 bar, this will also become 1 1. So 1 1 means everything will toggle, so it will be 1 0 1. Okay, in the 8th cycle, what happens? It is 0 0, then q0 q1 bar, sorry, q0 bar, q0 bar will be 0, so it will be 0 0, and q0 bar, q1 bar, that will be 0 0. Okay, so that means it will remain fixed. Have I made any mistakes? See this thing, it is j0 k0 is 1 1. Okay, and here it will be j1 k1 will be, that will be 1 1. Okay, and this j2 k2, that will be, j2 k2 will be q0 bar, that is 1, q1 bar, that is 0. Oh, this will be 0 0. Okay, 0 0. Okay, so it will be 0, this will be 0, remain the same, 0 0 1. And then in the next it is 1 1. Okay, this will be q0 bar, that is 0 0, and this is q1 bar, q0 bar, that is also 0 0. So it will remain same, it will also remain same, and it will change, that is 0 0. Now see, there the repetitive nature comes. Okay, so previously it was 0 0 0, and now after this it got again 0 0 0. So from here to here. Okay, so that means that after one cycle, two cycle, 3 4 5 6 7 8 cycle, there are how many different states? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. So 8 number of different states are possible. That means the modulus is 8. So the correct answer will be, what is the modular number of the counter described in question 9? It will be 8. Okay, so here the modulus will be 8, mod 8 counter. Okay, mod 8 counter. Okay, in the next question, if the initial state of the question 9 is 0 0 0, the same question, what is the state after 28 clock pulses? So if there are 28 clock pulses, so what will be the state? So after 8 clock pulses, the repetitive nature will come. That means if it is 0 0 0, so after 8 clock pulses it will again come 0 0 0. After 16 clock pulses it will again come 0 0 0. After 24 clock pulses it will again come 0 0 0, and then plus 4 clock pulses, again plus 4 clock pulses it will come. After 4th clock pulses, after 4th clock pulses it will come 1 0 0. This is 1 0 0. Okay, so after 4th clock pulses it will come 1 0 0. So it will come as 1 0 0. So the correct answer will be option D. So suppose there is a n number of clock pulses, how you need to calculate? Because we know that the periodicity is 8 after 8 clock pulses. So if we divide 28 by 8, so 3 8s are 24 and 4 is remaining. So we should, so after this periodicity we have started from 0 0 0. Okay, so we can see that whatever is the remainder after that many clock pulses, what is the output? So that will be the answer, correct answer. Okay, so here also the correct answer is 1 0 0. Yeah. Okay, the next question, if the Q2 output of the counter described in question 9 is considered as the MSB and Q0 as the LSB, how would we describe this counter? Okay, so which counter it is talking about? This counter. Okay, the same question. So in the question 9, so here the Q2 is MSB and Q0 is LSB. Okay, so here in the truth table, Q2 is MSB, Q2 is MSB, and Q0 is LSB. So if it is MSB and LSB, then how can it count? Okay, so after first clock pulses it will count 7, right? 1 means 7. Then in the second clock pulse it will count 6, then it will 5, this will be 4, this will be 3, this will be 2, this will be 1, this will be 0. Again if we do it again, see, so it is 1 1, so it is 1 1, and here 0 bar, that means it will be 1 1, and here q1 bar, q0 bar, that will be 1 1, so it is 9. So here again it will come 1 1 1 totally. So here again it will start from 7 counting. So this is counting from 7 to 0, so this is a down counter. So this is a down counter for sure. Okay, so now in the given question it is asked so it will be not be a up counter, so it is not up counter, this is not counter, so this is a down counter and this is also down counter. Now it is saying a 3-bit binary. 3 bit means how many flip flops are there, that much bit it will be, right? It is 1 bit, it is 2 bit, total, in total 2 bit, and in total it is the 3 bit, and single it is 1 bit. Okay, so this is 3 bit, but here the clock is synchronous because the same clock is moving to each of the flip flop, so that means it is a synchronous one. So the correct answer will be 3-bit binary synchronous down counter. 3 bit because there are 3 flip flops. Binary so binary, you know, right? 0 and 1. Synchronous because same clock pulse in each of the flip flop. Okay, and then it is a down counter. Down counter because counting from 7 to 0 and again 7 to 0, like this. Okay, so 3 bit because 3 flip flop of this thing. Okay, so the correct answer will be option D. Okay, the next question. The counter shown QC, QB, QA is 0001 of its state. What is the modulo number of this counter? So similar thing we need to do. We need to find the same thing. Suppose, so here what is happening, see, we know the JK truth table. At first we need to draw the JK truth table. This is JK, this is Qn plus 1, this is Qn plus 1 bar, and there is some remarks. Okay, so it is 0001 10 and it is 11. So this 00 means this will be Qn bar, that is no change. This is 01, this is known as reset. This is 10, this is known as set, and 11 means this will be toggle. Yes. Okay, now we need to know that what is the JA and KA, both are equal to 1. This is 1 and this is 1. Okay, JB and KB are input from QA and QC, so it will be QA XOR QC. Okay, and then JC is nothing but QA bar and QB, and KC is QB bar. Okay, now we have to draw clock pulse. JC, KC, JB, KB, JA, KA, QC, QB, QA. Okay, so we have to find out the modulo, means after how much the value repeats. Okay, so previously it will starts from 000. Okay, this starts from 000, so it will start from 000. There was no clock, no JCKC, JBKB, JK. So in the next JK is 11, so it is 11. JBKB is equal to QS or QC, QS or QC 0 0, that means it will remain 0 0. And JC is QA bar into B, QB, that is 0. And then again KC becomes QB bar, that is 1. Okay, so this is after first clock pulse. So what will be the answer? If JC is 0 1, the output will be JC is 0 1. See, JK is 0 1, the output will be 0, right? So it will be 0, it will be 0 0, that means no change. 1 1 means toggle, that is 1. Okay, after the second clock pulse, see what happens. So this is JAKA 1 1, this is QA XOR QC, QA XOR QC 0 and 1, that means it will be 1 1. JC is QA bar QB, QA bar is 0 into QB, 0 into 0, that means it will be 0, QB bar means 1. Okay, so 0 1 means it will 0, 1 1 means toggle this thing. Okay, after third clock pulse, what is happening? JAKA, it is 1 and 1. Okay, so it is 1 and 1. And then JBKB is QA bar into QB, QA bar means 1. Okay, into QB, it is 1. So this is 1 1. Okay, and JC is QA bar, sorry, JBKB is QA XOR QC, QA XOR QC. Oh, so this will be 0 0, right? This will be 0 0. Okay, and then here JC is QA bar into QB, QA bar means 1 into QB, that means it will be 1, and it will be QB bar, that will be 0. So 1 0 means the output will be 1, 0 0 means the same thing, that is 1, and 1 1 means toggle, that means it is 1. Okay, so this is the third clock pulse. If we consider the fourth clock pulse, then how it happens? See, JK is 1 1. Okay, now it is QA and QC. This is 1 1, so it will be 0 is 0 0, right? 1 0 1 is 0. And then JC is equal to QA bar, which is 0, so it will be 0. QB bar, that will be 0, that means it will be 0 0 0 means no change, that is 1. This is the no change, and this is toggle, it is 1 1 0. Okay, yeah. The next thing is 5. After fifth clock pulse, what happens? This is 1 1. Okay, QA and QC XOR, this will turn to 1 1, and then it will be QA bar into QB, that means it will be 1, QB bar will be 0, so that means it will be 1, it will toggle, and it will toggle. Now also none of these things are repeating. Okay, okay, so after 6 clock pulses, JAKA both are 1 1. Okay, and then JBKB is QA or QC, that will be 0 0, and then JC will be QA bar, that is 0, that means it will be 0, and KC is QB bar, that is 1, that means 1, so it will be 0 0 0 means it will remain same, and 1 1 means it remains top. Okay, so see, this thing again repeats. Okay, so if we consider this thing 0 0 0, it again repeats here. Then if we move forward, suppose after the 7th cycle, it will be 0 1 0 0 1 1, the same thing, and it will be 0 0 1, sorry, 0 0, and it will be 1. Okay, 0 0. So the same thing is repeating after 1 2 3 4 5 6 clock pulses. So the question is, what is the modulo number of this counter? So there are 6 different states: 0 0 1 0 1 0 1 1 1 1 1 0 1 0 1 0 0 0. So 1 2 3 4 5 6. So the correct answer will be 6. What is the modulo number of this counter? So the correct answer will be option 6. Option B. Okay, 6. So see how we should solve this problem. We should at first draw the truth table of the respective flip-flop, what it is given, the truth table of the respective flip-flop, and then we need to find out what is the input for each of the flip-flop, and we should write the equation, and after that, after each clock pulse, we should calculate this and we should find the result. Okay. Okay. And the last question. So here it's the same question, the counter describing question for what is the state after 4 clock pulses. So after fourth clock pulses, the output will be 110. Okay, it will be 110. Okay, so the correct option will be 110. That is answer number A. Yeah. Okay. Okay, so that was the last question. So actually you should practice this too much so that it can be solved within like 10-15 seconds each of the question. So it is very easy, but you have to be actually very accurate to get the output, because if you missed a single digit, then the whole answers will deviate from the original answer. Okay, so okay, that's fine. So this is all for today. Thank you. So I am ending this meeting.